Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part two of the lecture on regional skew. This is the 10th lecture in the Statistical Methods and Hydrology class. Right, so in our list of topics, we are on trading space for time. Okay, so the basic idea is that we have difficulty estimating the skew coefficient because we don't have enough data. Our samples are too small. And we create our sample by spanning data across time. So too small a sample means not enough time. So we're going to try to improve our estimates by doing the equivalent of bringing in data from other independent stations and spanning space to have a bigger data set and be able to get a better estimate, right? So effectively, this would be reducing our time sampling error and converting it over to spatial sampling error. And the spatial sampling error becomes a function only of the number of stations. So our assumptions thus far, we're down to having spatial sampling error instead of time sampling error. And the spatial sampling error is due only to the random pattern of storms within a region. Right? So let's say we are considering two equivalent watersheds in the same area, and a major storm passes over one of them. This is a storm that could pass over either of them because we're considering these to be meteorologically homogeneous, but the storm passes over one and not the other. And the result is that the skew coefficient in the watershed that received the storm is going to be much higher than the skew coefficient in the one that didn't receive the storm. And if this is a very large storm, maybe larger than you would expect from the record length, the skew is going to be too high in the watershed that received it and too low in the watershed that didn't receive it. Right? So one way to cure this problem and to kind of spread the effect of that big event over both watersheds would be to just average the computed skew coefficient from both of them. With that logic, then the greater the number of stations that we use, the smaller the spatial sampling error is going to be, right? The smaller the error due to the random positioning of storms is going to be, right? More stations reduce that element of sampling error, right? But what's the problem? Right, that sounded good, but the problem is that the basins are not truly equivalent, okay? So we might have meteorologically homogeneous areas, but skew is also very dependent on the shape of the watersheds, okay? So spatial sampling error is actually a function of both the number of stations and the differences in the basin characteristics. So we're gonna have spatial sampling error either way because skew is a function of basin shape. Right, so let's take a look at the factors that influence skew. So let's first look at large positive skew coefficients, right? So here's a PDF with a positive skew. We can have some very large events, right? The physical characteristics that lead to large positive skew and large events would be watersheds with steep slopes, with generally low infiltration rates and fast conveyance through the system, maybe a location downstream of two major tributaries where we get events coming from both at the same time, which can add together, right? So things that can make a flood event much, much larger than the events often are in that watershed. Now, statistically, what can give us a positive skew is one or more rare events in a short record, like we saw with the double hurricanes. Also, mixed populations can give us a positive skew because we end up with a frequency curve that's kind of boomerang shaped with some really large events on the upper end because they're from a different population. Okay, what about negative skews? All right, so large negative skew coefficients in watersheds. Here's a distribution with a negative skew down here, and the upper tail is now kind of truncated, showing that events really don't get that much larger than the typical events, right? So what might cause large negative skew coefficients in the watershed? Physically, we're looking at low average basin slopes, wide drainage areas, a large percentage of area controlled by lakes and swamps, high channel losses, generally high infiltration rates. So various things that make it take longer for water to get to the channel and keep from having high peaks. Right now, statistically, what causes a negative skew would be one or more very low events. Wow, rather suddenly, that's the end of video number 2. And I will see you in video number 3 on guidelines for doing regional skew studies.